Welcome back to our series on the 4 fundamental forces of physics. Today we're talking about gravitation, the force that you and I probably have the closest working relationship with. But it's not only what sticks you to the ground and makes you fall down, it also explains how stars and galaxies form, and it will describe how they die. But even though we can watch it in action, gravitation is much more complicated than it appears. Generally, I think of gravitation in two different ways: the way that Isaac Newton described it, and the way that Albert Einstein described it. In classical Newtonian terms, gravitation attracts everything in the universe that has mass to everything else in the universe that has mass. And I mean everything, from tiny particles to galaxies. It's universal and treats everything the same. But the strength of this attraction depends on the object's masses and the distance between them. The more massive an object, the greater the gravitational force it exerts on another, and the force decreases rapidly the farther apart the two objects are. Isaac described it this way: the force of gravitation is proportional to the product of the object's masses and inversely proportional to the square of the distance between them. Newton's mass and distance-based understanding of gravitation is really useful for stuff like predicting the existence of Uranus based on the movement of Neptune, but it doesn't explain everything, like Mercury's orbit. Trouble with Mercury is that the point where it's closest to the Sun, its perihelion, isn't where Newton's law predicts. It took an Einstein to explain that. Actually, it took Albert Einstein. Einstein described gravity as a property not just of mass, but also of space and time. He envisioned space-time as the fabric of the universe, and his theory of general relativity basically says that objects that either have mass or energy distort that fabric. Think of a watermelon and an orange on a mattress. Each makes a depression in the mattress, and if the orange rolls toward the watermelon, it will accelerate as it reaches the depression made by the more massive fruit. The attractive force thus gets weaker or stronger depending on the distance between the fruits. It's like Newton's law on steroids. Gravitation is the warp in space-time created by mass or energy. So in the case of Mercury, the closer it gets to the Sun, the more the Sun's huge mass curves space-time, which effectively causes that point of perihelion to move. You'll notice that this applies to objects with mass or energy. Einstein discovered that gravitation can also influence energetic but massless stuff like light if the force is strong enough. For instance, he observed that light bends around really massive planets and stars, and his theory of general relativity predicts correctly that a compact enough mass could distort space-time so much that light could not escape it. And that is a black hole. Now remember that for each fundamental force, there is a particle, a force carrier, that essentially conveys force between bodies. But if light responds to gravitation, its force carrier must be really tiny. Gravitation is described as being carried by massless particles, called gravitons, but unlike other force carriers we've talked about, like pions and gluons, gravitons are theoretical. They've never been detected, and they are predicted to be essentially unobservable. We're only able to witness their handiwork, and that is gravitation. We hope that you enjoyed our series on the 4 fundamental forces of physics. If you have questions or ideas for other stuff we should be talking about, we're available on Facebook or Twitter or in the YouTube comments below. Goodbye.